All right. Hi, everyone. Welcome to the online causal inference seminar. Today we have Richard Guo from University of Cambridge presenting on confounder selection via iterative graph expansion. Our discussant today will be Ilya Shpitser from Johns Hopkins University, and we'll stick to the standard format for discussion. We also have in the Q&A, Qingyuan Zhao, one of our own, is the co-author on this paper, and so he'll also be answering some questions. So now I'll switch to Ying, who will be handling questions today. All right, Ying.
Thank you, Emma. So as usual, we will use the Q&A section for submitting questions. Richard will also have places to stop for questions, but we encourage you to submit your questions as soon as you have them. Please do submit it using the Q&A button at the bottom of the Zoom window instead of the chat for us to better track the questions. So I think that's all. Please feel free to get started, Richard.
Right. Yeah, I want to thank the organizers for having me and also for running this fantastic seminar series. Very happy to be here to present my recent work on confounder selection by iterative graph expansion. And this is joint work with my colleague, Qingyuan Zhao, who will be handling the Q&A. So this is the outline. I'll start with some introduction and show you a Shiny app demo that implements our method, and then I will tell you why that works with some theory. Okay, so let me start with the introduction. So confounder selection is a very important and basic problem in observational study. I think you would agree with me. The single most widely used method for control for confounding, for identification, is this adjustment, covariate adjustment. So throughout the talk, I will assume we have a point treatment that is X and a single outcome that is Y, and that we're interested in inferring the effect of X on Y. And the strategy I mentioned is just through adjustment, a set of covariates S. The S should satisfy the so-called conditional exchangeability, meaning that the potential outcome Y indexed by this X is independent of X in every stratum defined by such a covariate set S for every treatment level X. And once you have this condition, then under further assumption about the positivity of the treatment level, we can identify, basically on the left, you have this causal query, on the right, you have this observed condition distribution, and that is the basic idea, the underlying the identification of many effects, such as the average treatment effect and average effect on the treated. So then the million-dollar question is, how do we select such a set of covariates S under which this conditional exchangeability holds? And this is the problem of confounder selection. And it can be argued that there are slight variations of the objectives depending on what we're talking about. So the primary objective would be how to find such a set of observed covariates such that it satisfies this conditional exchangeability condition. And such a set is called a sufficient adjustment set. And also, there are a bunch of secondary objectives, and that is when you have multiple choices of sufficient adjustment sets, and you can further choose one to optimize some specific criterion, such as efficiency, the cardinality of the set, and the cost of data collection, for example. And these are all very interesting problems, and they have been considered in the literature. But for now, I'm going to set that aside. So for this talk, I'm going to only focus on the primary objective, namely finding a set S for which this conditional exchangeability holds. Okay, so more or less, I'm going to talk about this problem in a graphical framework. Namely, I assume there is an underlying DAG that defines the causal model. So you can think of the causal model as the structural equation model with independent error defined by such a DAG model. Or actually, if you want, you can think about the even weaker model that is the FRCI-STG model associated with the underlying DAG. And I want to think about there exists such an underlying DAG that defines the causal model. So I guess the immediate reaction, which is, I won't be surprised by the audience if anyone finds this solve the problem. Basically, Pearl in '93 has a path-breaking paper about the backdoor criterion that says if S is a set of covariates excluding the treatment and outcome, is a sufficient adjustment set if satisfies two conditions. The first condition is that the set contains no descendant of X, which is understandable because you don't want to block any directed pathway from X to Y. So this is the first condition. The second condition is the more pronounced one, namely, such a set should block all the backdoor paths between X and Y. So what is a backdoor path? The backdoor path is a path with an arrowhead into X. So we should define S such that there is no M-connected paths between X and Y with an arrowhead into X. So these two conditions is called the so-called backdoor criterion. And the reverse side of the story is that this criterion is actually complete in the following sense, as proved by Shpitser et al. So if S is a sufficient adjustment set for the causal model defined a certain graph, then if I remove those descendant of the treatment from the set S, then the remaining set is still adjustment set and it satisfies the backdoor criterion. So in practice, and which is also what I'm going to take in this talk, I only consider adjustment sets that contain no descendants of X. Without loss of generality, we can always restrict the search for adjustment sets to those that contain no descendants of X. So under this assumption, then any set is a sufficient adjustment set if and only if that meets a backdoor criteria. So indeed, this is an if and only if condition. So it does look like a solved problem, isn't it? I guess just to provide a bit motivation about this work, I think this bears out of conversation with my co-author Qing Yuan, because I think in the graphical model perspective, frequently, in the paper we say, suppose we have an underlying DAG or ADMG model G, and then we're going to derive a bunch of results, make statements, and sometimes the statements would involve properties about this G. So then it brings up this question, so where does the G come from? In what cases we can expect knowing such a graph G? I think it's quite rare in practice. So basically, I think the motivation is coming from some critiques on this known G stance. So at least I'm going to provide critiques in two aspects. So firstly, it is perhaps not practical to assume that you know the underlying graph G, because probably we don't know the full causal structure or mechanism. And take it further, suppose we know it, but it probably another matter if we can readily draw the full graph. Because firstly, where do we set the boundary of my canvas? So what that means is you can always add more vertices to the graph and you don't know where to stop. Well, some people would argue, you want to include common causes, but common causes are still common causes. So, you could imagine going, to the origin of the universe, and that would be way too many vertices to draw. And there is another analogy I want to make. So suppose you're quite organized person, you know where your toothbrushes are, you can find where your computer, your home. But if I ask you to draw out the floor plan of your home, so it's probably another matter. So even if you have the rough idea of how things are related, but it could be another matter to draw it completely on a pen and paper. So, and also frequently, it's not the statisticians who are supposed to draw the graph. We're more or less rely on the domain knowledge from domain experts to draw the graph. I would want to say that there are tools and protocols that kind of formalize or aid the process of drawing the DAG model. But I think many people still find this practice quite challenging. So this is the first aspect of critique, namely, it is not entirely practical. Well, the second aspect is just a simple observation, nor is it entirely necessary. Because if you think about the backdoor criterion, which consists of two clauses, it certainly only concerns partial knowledge about the graph. Knowing a set satisfies the backdoor criterion does not really let you to fully recover the graph. So the backdoor criterion by itself is only a statement about certain aspects about the graph G. So naturally, then there are two further questions. And so the first question is, how can we articulate what is the partial knowledge about the graph G that defines the backdoor criterion? And namely, can we find a proper modular representation to such a partial knowledge? Then the further question is, having defined such a representation, how do we design a procedure to properly elicit such a partial knowledge from domain experts? Okay, so before I present our method, it's worth mentioning that there are other works, earlier proposals in literature that move away from the known G stance. And a particular example, I think is a quite well-known one, is this disjunctive criterion proposed by Shpitser. So imagine a setting, you have already collected a data set. In the data set, you have the treatment X, you have outcome Y, and you also have collected the data for a bunch of observed pre-treatment covariates. Then you go through this table to ask for each covariate whether the covariate is either a cause of X or a cause of Y, or both. If the answer is yes, you include that covariate into the set S. So this is a disjunctive criterion. And Shpitser proved a quite remarkable property, which is the set S would be a sufficient adjustment set whenever the set of observed pre-treatment covariates contains any subset, and the subset is a sufficient adjustment set. So as you can imagine, this can be quite useful, especially when you are in a scenario where the data set has already been defined, the data has already been collected, and you only have very limited structural knowledge about the underlying graph. Namely, you only know whether or not every covariate is a cause of X or Y. In that case, then using this criterion, may be the best bet. But on the contrary, if we're in the early stage of designing the procedure, where part of the goal is to figure out what covariates we want to measure, then this is probably not the most suitable. Okay, so let me just give a nutshell description of our approach to give you a feel what a proposal looks like. So for this purpose, I'm going to look at this so-called butterfly bias graph, where X is the treatment, Y is the outcome, and B is this confounder of X, Y. And the so-called butterfly is evident from this M-shaped path X, C, B, D, Y. So basically, we need to control B, and once control B, that opens this aimed shaped collider path, and we either have to additionally control C or control D in order to control the confounding between X and Y. Okay, well, in terms of our procedure, I will first draw X and Y with a bidirected dashed edge between them. So I will explain what this symbol means later, but for now, you just think about this means potential confounding. So this symbol simply means there could be potential direct confounding between X and Y. So in the next step, I'm going to introduce this variable B. By introduction of B, this potential confounding between X and Y is gone. B is introduced into the canvas, and at the same time, I need to draw new edges. I need to draw the edges between B and X and B and Y, indicating that there could be potentially confounding between B and X and B and Y. In the next stage, I'm going to try to control this potential confounding between B and X. For that purpose, I'm going to introduce C that breaks the B and X link, but also introduces new links. And I continue to try to control the edge between C and X. Immediately, when I find that there is no confounding between C and X, I remove the edge between C and X. And right now, lo and behold, X and Y are in different connected components, meaning that X and Y are disconnected. And immediately, we know B and C is found as a sufficient adjustment set. Okay, so in terms of the two previous questions, First, the representation of the partial knowledge to define the backdoor criterion. Our representation is a specific graph with bidirected edges. In particular, this dashed bidirected edges denote a potential confounding arc, which I'll define in a moment. And the second question about the procedural design, how do we elicit such a partial knowledge? So basically, this is an iterative procedure. Every time we select a possible confounding arc and introduce new variables to control such a confounding arc. The new variables introduced to control it are called a primary adjustment set. And the way to conceptualize primary adjustment set is through some queries from the user about the common causes and mediators. And then I'm going to remove that potential confounding arc and also introduce new arcs. This procedure would terminate once X and Y become disconnected. At that stage, we declare a sufficient adjustment is found. A sufficient adjustment is all the variables on the canvas except X and Y. And then you can think of this as a procedure of inverting the latent projection. Okay, so I think now it's due time to show you a demo. So I have this demo coded up in R Shiny. Okay. Now I'm going to switch to my demo screen. Okay, I guess you guys can see it now. All right. So here I'm looking at a case study on the right. So the case study is about inferring the effect of warm-up and on the sports injury. So whether or not you do warm-up before exercise would increase or decrease the likelihood of getting sports injury. So treatment is a warm-up, injury is the outcome. And here, this example, by the way, from Schreier-Platt 2008 paper. And I'm coloring all the observed variables as blue and all the unobserved latent variables as red. Okay, so for now, I'm just showing you, suppose this is the underlying true causal DAG. But the point is you want to imagine yourself as a domain expert who has, knowledge about the mechanism of sports injury. In your mind somewhere, there is sufficient knowledge about this graph, but you may not be able to immediately draw the full graph. What I'm going to do is to query you repeatedly about certain aspects of the graph. Okay, so this is the Shiny app. Firstly, I'm going to rename the treatment as warm-up. Rename the outcome as Y. So the goal here, as we remember, is to try to make the warm-up and injury disconnected by directed edges. Immediately that happens, we have found a sufficient adjustment set. So there is only one edge between warm-up and injury. Let me try to see what I can do with that edge. So I double-click on the edge. So ask me, is there a primary adjustment set for warm-up and injury? I don't know what that means, so help me find one. Okay, ask me, is there a common cause of warm-up and injury? So imagine I'm a domain expert. So at least, there are three common causes. The coach is a common cause, the genetics is a common cause, and the fitness level is a common cause. So I say yes. Enter common cause. Let's say I enter fitness level. Okay, fitness level observed? No. Remember, only blue vertices observed. So now it starts to ask me about mediators. So is there a set of observed variables, a fully mediated effect from fitness level on the warm-up, where the fitness level could affect warm-up through this unobserved variable? So I would say no. Is there a set of observed variables, a fully mediated effect of fitness level on the injury? Well, if I think about it, fitness level only affects the injury through this muscle fatigue, and the muscle fatigue is observed. So I would say muscle fatigue. These are my mediators. Now, he asks me again, if there's another common cause of warm-up injury that is not blocked by muscle fatigue. Well, obviously, genetics is another common cause, and genetics affects warm-up through this pathway of unobserved variables, and genetics also affects injury in at least 3 pathways, this one, that one, and also through this tissue disorder, tissue weakness pathway, and that pathway is not blocked by muscle fatigue. So I say yes. So I key in genetics. Genetics is not observed. So genetics to warm up, no, I can't find mediators. But for genetics to injury, there are 2 mediators that fully mediate. One of them is muscle fatigue. The other one is a new one, is the tissue disorder. So I just key in tissue disorder. So I think these will suffice. I click, these are my mediators. Now ask me again, is there a common cause of warm-up injury that are not blocked by muscle fatigue and tissue disorder? Well, there's another common cause, which is coach, but if I think about it, well, I mean, coach only affects the outcome injury through the muscle fatigue. So no, there's no more common cause. So now it's a smiley face. It tells me this wizard has gone through, it has found the primary adjustment set for this dashed bidirectional confounding arc between warm-up and injury, and that set is muscle fatigue and tissue disorder. I say yes. So what it does is to remove the bidirectional confounding arc between the variables and introduce the fatigue and tissue disorder onto the canvas. At the same time, also introduce 5 edges, including these 2 edges, those 2 edges, and also a bidirectional edge between muscle fatigue and tissue disorder. Now you can see there are 4 edges that are highlighted, and on the bottom right, it tells me that in order to render the warm-up and injury disconnected, at least 2 edges I need to remove. I either at the minimum remove these 2 or remove those 2, but I can choose which one I want to remove in practice. For example, if I want to just look at the edge between muscle fatigue and tissue disorder, okay, I click on the wizard. Is there a common cause of them? And the answer is yes. And the common cause of them would be genetics. Is genetics observed? No. Does genetics allow me to control this confounding arc through mediators? Unfortunately, no. So now that would render this bidirected potential confounding arc as an uncontrollable solid confounding arc. That means this edge by no means I can remove. So then I need to think about the other edges. So either these 2 or those 2. Let's say I look at warm-up and muscle fatigue. So is there a common cause of muscle fatigue and warm-up that is not blocked by tissue disorder? Yes. And that one could be fitness level. Fitness level not observed. And also, unfortunately, I don't have mediators to control the fitness level pathways to these 2 vertices. So I say no and no. So this edge is also not expandable. The same way, if I look at the edge between warm-up and tissue disorder, also, I think similarly, there won't be a primary adjustment set. So my only bet insofar is to control simultaneously these 2 edges. So if I look at tissue disorder and injury, is there a common cause of tissue disorder and injury that is not blocked by warm-up and muscle fatigue? Well, they do have a common cause. The common cause is genetics, but genetics effects on the injury is fully mediated by the muscle fatigue. So the answer is no. So that means I'm ready to remove this set by introducing no more variable. So I say yes. So there's only one edge left to cut, this one. Similarly, is there a common cause of muscle fatigue and injury that is not blocked by warm-up and tissue disorder? Well, there's genetics, but genetics is fully mediated by tissue disorder. So I say no. So I can remove this edge. So now warm-up, injury live on different kinetic components. That means these two variables, muscle fatigue and tissue disorder, is found to be a sufficient adjustment set. Okay, let me get back to my slides. Okay, I hope this gives you some idea how this operationalizes. So let me just comment on some features of this procedure and its implementation. So we have, so this is a graph, our representation is a graph, then edges are called confounding arcs. There are two types. The dashed ones are potential or possible confounding arcs, and the solid ones are uncontrollable confounding arcs, meaning there is no primary adjustment set I could use to control it. So to control the dashed ones, we need to ask the user a bunch of questions to elicit the knowledge. And I think it has been clear to you, hopefully, that to answer these queries, you do not need to pre-specify the full graph. Although I show you the full graph, that is just to conceptualize what might be in one's head. So actually, to answer the questions, as you could notice, the only thing you need to reason about are common causes and mediators. And these are things you can reason about local structures and not about global structures. And the queries are designed to be economical. What that means is that we only query those information that is needed for the task here. For example, the causal relations between those observed confounders, we never ask about them because they're irrelevant to our task of confounding selection. And also, I think the procedure is designed in a way such that users' familiarity with causal graphical model is not a prerequisite. So in particular, the user does not need to be aware what a collider bias is. And implicitly, it is already taken care of by this procedure. So probably you already noticed here, the muscle fatigue is actually a collider. If you condition on muscle fatigue, that would open up this M-shaped collider pathway like this. But the procedure would also ask us to control for tissue disorder that would block this collider pathway. So it is already taken care of. So there are two ways that the procedure can terminate. The first one is, as we already seen, that the X and Y are disconnected by bidirected edges. That means a sufficient adjustment set has been identified. But if you are unlucky or you don't have sufficient observed variables, then you could possibly run into the case where the X and Y are connected by uncontrollable confounding arcs. That means no sufficient adjustment set can be found. Okay, before I move on to the theory, is there any question?
No, we currently don't have public questions. Please submit your questions as soon as you have it, and yeah, we'll have to. Okay, Emma has a question.
Yeah, I have a question. Is there a way to show the intermediate process? Because what the algorithm currently is doing is it's in the background, computing something or drawing something for itself or something. So is there a way to show that? Because it seems to be difficult to keep all of this in your head in answering the series of questions.
Okay, so I will say two things. One, I haven't explained why that works. Probably it's already clear to you, Emma, but I guess if you see the theory, it will become clear what the algorithm is trying to do. The second thing is, I think engineering-wise, you probably notice I have keyed in genetics twice. I shouldn't have done it. I think there are definitely some room for improvement for the engineering that the user would only need to key in less information than its current implementation. I don't know if that answers your question.
Yeah, that helps. Yeah, thanks.
I suppose there's another question.
Oh yes, a question just pops up. It asks, latent variables could be included in this model or only measured variables?
So we would ask questions about latent variables, in particular about latent common causes. But on the canvas, all you see are observed variables. So because those are what we need to control for confounding, what we use for constructing the sufficient adjustment set. So I hope that answers your question.
Thank you.
All right. If there's no more question, let me move on to the theory a little bit. Okay, so so the theory, I would assume there is this underlying acyclically directed mixed graph G over the vertex set V that defines our causal model. This ADMG is a direct extension of DAGs that allow for confounding that has bidirected edges in addition to directed edges. So an ADMG has directed edges would represent direct causal effects, and bidirected edges would represent the existence of latent common cause, in other words, endogeneity. So for ADMG, a very important concept is M connection and M separation. And this is a direct extension of the concept of deconnection and deseparation from DAGs. So the way to test M connection and M separation is basically the same as for testing deconnection and deseparation. And this induces a relation that can be posited from any set of triplet. So for A, B, and C, I suppose they're disjoint, there is a way to test whether A and B are M connected given C, or A and B are M separated given C, by testing whether there is an M connecting path between A and B given C. Okay, so I'm going to assume we're operating under an unknown graph G, but we can make repeated queries about certain aspects of G. Okay, let me introduce some notations. As you can see, this M separation or M connection is a statement about existence or a non-existence of certain paths, and there is no restriction about this paths except for its connectedness. But for our purpose, we're interested in confounding control, and that means we only care about certain shapes of paths. So the shapes can be defined in many ways. A particular aspect is whether or not a path has any collider. So collider is where two arrows meet. When the paths have no colliders, I call that an arc, and an arc is denoted with this squiggly line. So directed arc is just the synonym for directed path. So that means A followed by a bunch of edges, a bunch of arrows pointing to B. So directed arc means a directed path. And what is important to us is actually this confounding arc concept, meaning this is a non-collider path with endpoint arrows. So there are four configurations, either A followed by a bunch of left arrows, and then followed by a bunch of right arrows, and followed by endpoint B. Or A left arrows, bidirected edge B, or A bidirected edge, right arrows B, or A left arrows, bidirected edge, a single bidirected edge, and a bunch of right arrows, and to the other endpoint B. Okay, so confounding arc is kind of the basic building block for inducing confounding. And also, when we draw this arc notation, the actual paths that represent should match the endpoint arrowhead of this squiggly line. But if we don't want to restrict whether it's an endpoint tail or endpoint head, we can use this half arrow notation. So A half arrow, squiggly line, arrow B means either one of these two cases. And if we concatenate a bunch of arcs, that would define the path. And I use this wildcard notation for arcs, for concatenation of arcs. And that's a confounding path. A confounding path is represented in such a way. So you want to interpret this wildcard as meaning 0, 1, or more colliders. If there is 0 collider, that just means a confounding arc. When there's 1 collider, that means a concatenation of 2 confounding arcs. When there are more than 2 or more colliders, it is concatenation of 2 or more, 3 or more confounding arcs. And by the way, if we allow any shape of path, that is this specific symbol, half arrows with squiggly line. Okay, so having defined such shape of paths, then we can refine this notion of M connection or name separation by saying, by specifying particular shape of path. So that means existence or non-existence of an M connecting path of a particular shape between A and B given C. So M connection, M separation can be written in such a fashion because this type of half arrow path is meaning path of any shape. But importantly to us is a different 3 types of refined M connection or M separation relations, in particular the latter 2. So the confounding arc and the confounding path. So the confounding arc in our procedure that I just showed you in the demo translates into bidirected edges, and the confounding path is concatenation of multiple confounding arcs. So this notation, for example, the second one would mean given C, there exists a confounding arc that is M connected between A and B. I hope that's clear. Okay, using such a notation, we can basically reformulate Pearl's backdoor criterion in such a way. So a set S that contains no descendant of X satisfies the backdoor criterion if and only if there is no M-connected confounding path between X and Y given S. It's just a reformulation. Okay, but this is not directly usable because for blocking confounding paths, suppose C is a set that blocks confounding path. Because of this collider bias problem, if we enlarge the conditioning set, it's not necessarily true that A and B are still separated in terms of confounding paths. But what is true is for confounding arcs. When confounding arcs, we use a larger set to control for confounding arcs, that larger set always works. So it has its monotonicity. So basically, our idea is, because, as our notation suggests, any confounding path is a concatenation of confounding paths. So if we're able to block all the confounding arcs iteratively properly, then at the end of the day, I would be able to block all the confounding paths as well. And because confounding arcs are easier to conceptualize and block, that is the way we are going to proceed. So what is the set introduced to control a confounding arc? That is called a primary adjustment set, as you have already seen in the demo. So basically, the primary adjustment set between A and B is the set that renders the confounding arc between A and B disconnected. Okay, so as you can imagine, then we can keep adding vertices to this postulated confounder set S. But I guess as Emma alluded to, how do we keep track of the confounding relations? Actually, this has a simple answer because we're able to show something that is very useful. But before that, I'm going to see if there are any more questions.
We currently don't have open questions for now. So again, we encourage all the audience to submit the question as soon as you have them. But for now, I think we can continue.
Okay.
Thank you.
All right. So, okay. So what does the algorithm do to keep track of the confounding relations? So this bears relation to this important operation that is called latent projection. So if you remember, I said earlier on that our procedure can be viewed as running latent projection in the reverse. So what is latent projection? Latent projection is to represent a model of a margin. So ADMG, because the introduction of this bidirected edges, in addition to directed edges, it is closed. It is kind of the closed model under marginalization. So basically, if you can partition your vertices into observed V tilde and unobserved U, such as the V tilde and U are disjoint, then you can properly formulate a graph only involving those observed variables. Using this operation called latent projection, for example, suppose on the left, this is the full graph, then if I want to marginalize only onto the margin LXY, then I can keep these two directed edges and add two new edges, X to Y, because X to Y is only through the latent variable U2, and also add a boundary edge between L and Y, because that signalize that suggests a latent confounding between L and Y. Okay, so I think it's a pretty well-known result that M connection is preserved by latent projection operation, and what is key to our proposal is that we're able to show that the three refined M connection relations, the directed arc, the confounding arc, and the confounding paths, are also preserved by latent projection. And what our procedure relies on is a simple corollary of this theorem, meaning that if we take the latent projection, only take A, B, and the set of variables C, then a bidirected edge becomes a directed arc, becomes a directed edge. A confounding arc becomes a single bidirected edge, and a confounding path becomes a bidirected pathway. And this leads to what I call a representation. So we can, from the corollary, we can derive the district criterion. So on the left, it is Pearl's backdoor criterion. So S is sufficient adjustment set, if and only if it blocks all the backdoor paths in G. And this is a statement made about sort of the global property about G. On the right, we have this reformulation. Basically, we take X and Y and the posited adjustment set S. I only project onto that margin. Then on the projection, S is sufficient adjustment set if and only if there is no confounding arc that connects X and Y. So that is why the procedure would successfully terminate once X and Y becomes disconnected. Okay, so as I said, this leads to explicit representation and procedure. So what do we need to take care of? We basically need to track for any pair of vertices whether or not there exists a M-connected confounding arc between them, given all the other variables on the canvas. And when we draw the edges, we initially draw them as potential confounding arcs. If there exists a primary adjustment set, the edge is removed. Otherwise, the edge becomes an uncontrolled confounding arc that is written as this solid bidirected edge. And in particular, primary adjustment set can be constructed from the wizard I just showed you, and that only requires answering questions about common causes and mediators. Okay, so I don't think I have time to go through this, but basically, we can show the soundness of a completeness of our algorithm if we formalize it in this way. So if we run the procedure exhaustively, and also we replace the user's answer by an oracle, a truthful oracle, then we can show our procedure is sound in the sense that anything found by the procedure is indeed a sufficient adjustment set. And also we can show is complete, meaning that if all the, so if the oracle answers the queries in an optimal way, then all the adjustment sets, then the procedure is able to find all the kind of the optimal minimal adjustment sets. Okay, let me try to wrap up. So I think we introduced this notion of confounding path and confounding arc, which are quite useful to our development because that leads to a concrete representation of this partial knowledge. And also, I think this provides a structural definition of what a confounding is. And this complements, I think, some earlier efforts in the literature on the definition of a confounder or a confounding variable. And the queries are designed to be economical. So for example, there are certain things that are useless and we never ask about them. And the user does not need to be an expert or knowing anything about M separation or D separation to be able to use this procedure. All she or he has to do is to reason about common causes and mediators. In particular, the user does not need to be aware of this collider bias, which can be quite difficult to beginners about in graphical models. And also, I think this is a call to moving away to re-examine the stance of this known G assumption. So basically, I think a lot of identification problems only actually relies on certain partial knowledge about the graph, and it's worth thinking how to articulate the representation of such partial knowledge and how to elicit it. And I think more development is needed to use causal graphs for practitioners to design an observational study. Okay, thank you very much for your attention, and I would encourage everyone to try our Shiny procedure. Thanks.
Thank you, Richard, for the great talk. We have another question popping up, but Qingren is answering it, so Emma, should we proceed or? Okay.
Yeah, maybe we move on to the discussion in this case, and then hopefully we'll have some time for questions and answers after. All right,
Okay.
Ilya,
I guess that's
go
me,
for it.
right?
Yes, sorry, please go for it.
Just 1 second here. Let me go to the full screen. Hopefully you can see this. Is that right?
Yep.
Yes, yes,
Great.
it worked.
Excellent. So thank you for inviting me. It's always great to be at OCIS, and thank you, Richard, for a very thought-provoking talk. So I have actually relatively few things to say about this. So we'll see how this goes. I have one minor question and one comment. So it's funny. This is not the first time I've did an OCS discussion. I always seem to start with a variant of this slide, basically, with different bullet points at the bottom. So this is the usual story, right? With covariate adjustment, right? And lots of talks kind of start from this, and then they say, well, we're gonna elaborate on the story. And the elaboration here is, what do we do? How do we find C, the valid adjustment set, if the graph is complicated, or what do we do if the graph isn't known? Obviously, in this case, it's very obvious. And this is, again, a recap which Richard did a great job with. There's if the graph is known, you can use the Bagger criterion. You can include variables that are descendants of treatments because they won't necessarily block causal paths. And Emma of course knows all about this and has very nice papers on this. And why would you ever do that? Well, because you might be uncertain about whether something is a descendant of a treatment or not, in the spirit of not completely knowing the graph. So this very, very often happens with electronic health records, for example, where timestamps are a little bit hazy, when something is measured. And so I think having these criteria that include descendants of treatments, I think is quite useful for giving a little bit more security about exactly what the ordering and the variables is. Also, this can come up, of course, if you don't know the graph. One approach is you learn it by model selection, and then you try to do something with the equivalence class. And there's some work in this, of course. And Emma has this work that can apply to the output of those algorithms as well. Okay, so the contribution in here is this interesting algorithm that constructs an adjustment set by asking questions, basically. So it's active learning, I guess, in the language of artificial intelligence, right? Active learning of something about the graph, basically. And so the nice thing is you don't need the structure. And also there is a definition of confounding in terms of paths, which is interesting. So first I have a minor question about this. So a naive question about defining confounding is, why isn't ignorability failing the definition of confounding? It's not graphical, not in terms of paths, But the thought here is, if ignorability holds, you don't have confounding. So consequently, if it fails, you do have confounding because you have to do something else, right? Now, that isn't to say that path definitions aren't useful, but it would have to be that they're providing some other something illuminating about this other than this. And of course, the advantage of this is you don't have to think in terms of the graph. You could just have an algebraic model, and you could have you could define presence of confounding in this way. Now, as Richard points out, confounders is very different from confounding, and it's a much trickier thing, which is why there's a whole separate paper on confounders. But for confounding, it's not clear to me that it's that tricky. Okay, so that's my very minor question. On expert solicitation, I do some expert solicitation myself, and of course, I'm a very graphical person, so a lot of my expert solicitation is like with doctors, and it's in terms of like drawing a picture on the board. My experience with this is, how easy are these questions exactly? Like, the claim is that they're pretty easy, but I'm not sure that they're so easy. They're certainly, I didn't find them so easy for myself when I thought about this procedure. And maybe that's just because I'm a graphical person. And the other thing I was going to say is, are these questions actually all for the expert or not? So here is this is a quote. I think I reproduced it from the paper correctly. This is what the paper claims you end up asking, right? So the first one, is there a common cause of C of A and Y such that neither its effect on A or its effect on Y is fully mediated by some set? So fine. And then the second question is this observed? And if first question is yes, second is no, what are some other variables, yada, yada, yada. And a lot of this is all about like whether things are being fully mediated. And this is where I got stuck on. First of all, this is a fairly complicated question, I think, to ask a person. Like, if I talk to the doctor, like, I can ask them like if A causes B, that I can ask. If I can ask if like, some set mediates A and B, they will probably tell me, but then I say, what about this variable? And I say, oh, right, of course, that variable will also be a mediator. So I think it's not so simple to get reliable answers to questions that are this complicated, basically. So that's my first comment. The other comment is 1 and 3 is about the model, 2 is about our state of knowledge. So they're not exactly the same. And I guess maybe it depends how you use this procedure. In the context of study design, maybe it makes sense to ask the expert, because you're not really asking whether it's observed, you're asking like whether we should observe it. But I do say that like in the context of like finding an adjustment set in an existing problem, I'm not sure that 2 is an expert question. It's a data question, right? And like speaking for myself, thinking about this procedure, I'm a graph person. I like to I feel fairly hobbled without drawing a DAG for a problem, and I think it's hard to answer in my head. And I think in some sense, it's kind of interesting. Like you end up using graph theory, but I think it's not in the graph spirit, in the sense that essentially what this is doing is it's replacing the graph by an algebraic description of the graph that's sufficient for finding adjustment, basically. Because a lot of these questions are basically algebraic claims about the model. That was my take on it. And I also think in practice, it's difficult to answer questions about full mediation in the affirmative. And I think it's a practical reason related to why Frondor hasn't been more widely adopted. Because I think like the Frondor method requires that you have a mediator that fully mediates everything, that isn't confounded. And I think in practice, it's just hard to find variables like this. That's been my experience. So my thought here is we should try to meet the subject matter in the middle. So covariate adjustment is very simple, very well studied, right? And the elicitation algorithm that's provided here, I think, is asking fairly complicated questions, really. And in computer science, we have this saying that if I have a human machine collaboration, then things should be hard for the machine and easy for the human, right? And so in that spirit, my open sort of question is it possible to ask easier questions at the price of using more complicated formulas for identification? Because we have very fancy theory for identification, of course, with graphs. We also have very fancy theory that can use additional non-graphical things like proximal inference or instrumental variables and all these other things. And so I just wanted to illustrate the kind of things you can do. So like the graph on the left is the Frondor graph. And the big difficulty with the Frondor graph is I need to find an M that's a full mediator, basically. And it's very difficult to find such an M, which you end up finding is an M that partially mediates the effect, but there is still the direct effect of A and Y. That's like the graph in the middle. And the point being that even though that's true, like you could still get identification with extra tricks. So the graph on the right, for example, if I have some proxies for the unobserved confounder Z and W, there are things I can do, despite the fact that the full mediation isn't achieved, right? So I think, like, I do wonder if you could use tricks like that to ask easier questions without requiring full mediation in particular. Basically. So that's I don't have anything like sort of constructive to say about it. I'm just sort of wondering about this. So that's all I really have to say. So to conclude, the usual way we think about identification is we know the graph exactly, and we ask our friend the ID algorithm or various extensions for what to do. We could try to learn the graph from data and then try to identify within the equivalence class. And we can also come up with simple criteria that require some limited knowledge. That's like what Tyler and I, in my paper, did back in the day. Or we can ask targeted questions, which is a very interesting new way of thinking about it, which is what this work proposes. It's model elicitation versus question, and I think it's quite promising potentially. And I think like the way to maybe extend this is to think about simpler questions, more complicated identification strategies, basically. And finally, thank you, Richard, for presenting. Always great to hear from you. It's very interesting stuff. I read the paper with interest. And here are some references. Not very important, really. And thank you very much for allowing me the opportunity to discuss. Always fun.
Thanks, Ilya. So yeah, Richard, Jian, do you want to say something or answer some questions?
I just want to thank Ilya. I think he always raises questions for us to think about, and with very good insights. Yeah, I just want to. I'm not going to. I definitely need more time to think about it. I just want to mention two things. First, confounding. I just find it interesting because that relates to the problem of representation. So I guess our philosophy is try to identify what exactly is the partial knowledge that is needed to test this backdoor criterion, and we arrived as such a representation, and it's nice to give a name to the basic structure that induces confounding, which is this confounding path idea. And in terms of questions, that I agree to some extent. I think for the mediation, perhaps not, it's hard to imagine, perhaps sometimes, but when you have an observed latent confounder, you have to try your best to even find proxies of such mediators to control for it. So I guess, and also I think that the questions are designed in a way that you only need to think about directed pathways. We never ask questions about colliders or any other shapes of pathways or even M-connectedness. So in that perspective, I think we have tried to some extent to simplify our questions, but maybe there's still room for improvement. So I don't know, Qingyuan, do you?
I just want to add one thing, perhaps, on the district criteria, because actually, when I think about this work, the most practical thing that may come out of it is the district criterion, which is you don't look at the full graph with many variables, some observed, some unobserved, to justify that you found a sufficient adjustment set. All you need to do is to look at the minimal graph, look at the minimal to latent projection graph, and check if the exposure and outcome can be connected by bidirected edges. It's a very easy criterion for verifying that a set is sufficient. And I think that potentially is more useful than the algorithm that we developed. I agree that algorithm involves some fairly complicated questions. But to me, I think these are kind of the questions you have to ask if you want to draw a graph, perhaps. And yeah, it's really, we are kind of exposing the difficulty of the assumptions behind that we claim a causal graph is null.
I know Emma has her hand up. I just wanted to make one brief remark on criterion. I haven't mentioned this in my slides, but I think it pretty straightforwardly follows from the definition of a Markov blanket. I'm not immediately aware of whether it was written up before or not, but yeah, anyways, yeah, I agree that it's very useful.
Is it okay if I ask a question? I hope, well, I guess I'm in charge, so it's okay.
Okay.
So I have a question that's something about the just a clarification. So would your algorithm output more than one set if more than one exists that you could use, or would it just stop when it identifies as primary? This relating to like this.
So that depends on how you run the algorithm. So basically, we have the algorithm as I show you in the demo, and we also have a formulated algorithm, which you try different ways you can expand the edges, because you could make different choices. And you also have an oracle that tells you all the primary adjustments set. I mean, for the latter, I think it would give you all the possible valid sufficient adjustment set. But in practice, we're using the former, right? The user is probably only going to do it once. Then, you know, I think it may not give you, you know,
Right.
to get another sufficient adjustment set. Basically, the user has to try again. You know, maybe.
Okay.
Yeah.
Yeah. So some follow-ups, I guess. So I was also wondering about this. So you are explicitly not using descendants, or you could have descendants that you allow, or
I'm
the beginning.
not using descendants.
Okay, great. That's and so is the idea behind this algorithm to like run it before conducting some type of observational study to know what you should measure, or is it like after you've already conducted the study, or when is the proposed use, I guess?
I think a certain advantage is to design. I think to design the stuff. I think it would also be used to post design analysis, but I think for designing is I think I would say is advantage.
Okay, great. Just curious.
Cool.
All right, great. Thank you, Richard and Chinyan and Ilya for all your discussion. I'll just wrap up for today. Okay. So thank you also to all the audience who is here and asked questions or just listened. Next week, we have Anish Agarwal from Columbia University talking about on-causal inference when temporal and spatial spillovers in panel data. So hope to see you all there and have a great rest of your week.
Yeah. See you, everyone.